Next week, can you turn in a rough draft of your synthesis report? I'd just like to see what you have done up to then. Today we're going to talk about the calculations for the kinetics lab. Also finish up chapter 14 and then just start chapter 19. Originally I had a lab scheduled, which is electrochem, but I think I'll postpone that lab a little bit later as we get closer to chapter 20. Well, let's take a look at the calculations for kinetics. In the kinetics lab, we look at this reaction, crystal violet and hydroxide, to form crystal violet hydroxide. And all we want to do for this lab is determine the rate law. In order to determine the rate law, we have to figure out what K is, and then M, which would be the order with respect to crystal violet, and then N, the order with respect to hydroxide. So we want K, M, and N. Well, different techniques for figuring out the rate law. And so let's take a look at the data that we have collected for this experiment. All right, this is the handout, sheet 3 here. And so you'll finish up the run 1 graphs and the run 2 graph. And then we'll go to the calculations here. These are the calculations. And so first off, we need the concentration for crystal violet standard. The concentration for the crystal violet standard is not what's given on this sheet. The crystal violet concentration, this is different units. It's 0.1596 grams per liter. I had to think about our balances. Our balances only measure to the nearest tenth of a milligram. So that's the precision of our balances. And so in a full liter, they only dissolved 0.1596, between a tenth and 2/10 of a gram of crystal violet chloride per liter. Well, crystal violet chloride has a molar mass of 408, and so we can convert the grams to moles and generate the molarity of crystal violet. And so I just had Excel do the calculation here. So in calculating the molarity, it's just taking the grams divided by the molar mass and get the moles. The volume doesn't change on the molarity. That's 10 to the minus 4 molar. It's actually quite small. to a very low concentration. How come we're using such a low concentration? Do you know why? Yeah, so we could see the reaction. I mean, we could use a higher concentration. Be a bit darker, right, the solution. Look like concentrated grape juice instead. But even though the concentration is so low, pretty intensely colored stuff. But the color has a lot to do with why it's so dilute. You know, it's so that we can actually see the reaction using a spectrometer. A spectrometer is going to measure absorbances. And if the absorbances get too high, then Beer's law fails. And so the reason this concentration was so low is to get it into the Beer's law region. And the Beer's law region is going to have an absorbance between 0 and 1. And so somebody figured this out. And so this is why they dissolved this much in there to get this particular concentration, or roughly this concentration. Now the sodium hydroxide, the crystal violet concentration is going to be 3.91 times 10 to the minus 4 molar. Actually, this is a standard solution, so this is good for decimals. We should be able to get 4 decimals here, 3912 times 10 to the minus 4 molar. The hydroxide concentration is 0.1018 molar. So let's go ahead and plug that in here. So the reason I set it up like this is so I can have Excel do the calculations. And so what we'll have to do is whenever we're mixing solutions together, in this case DI, sodium hydroxide, and crystal violet chloride, we have to factor in solution dilution. And so let's go to run 1 and put in the volumes of each. So in run 1, what was the volume of deionized water we used? Here. I have 15 here, but that's wrong. We did 10, 10, and 10. And 10. And so we have to factor in solution dilution. So here's the equation for this. The equation for this is written up here. So it's going to be a 10. This is what for hydroxide. It's going to be 10 over 30 dilution. C10 is 10 over 30 dilution of B5. Do you know what this dollar sign means? Have you seen the dollar sign in Excel? The dollar sign means do not change this. And so the 5 stays fixed. No matter if we copy and paste it anywhere, the 5 is going to stay. And so we want it to stay on row 5. I'll show you why in just a second. But here it is. This is B5. This is C10. And then I just typed in 30 because rather than sum that. All right. Now let's take a look at this equation here. What I'm going to do is I'm going to copy and paste it down. Because run 2, it's the same kind of dilution. When I copy and paste it down, we go from C10 to C11, because we're now in the next row. And so normally when we go C10 to C11, we would go B5 to B6, because everything would be shifted down 1. But since I put the dollar sign in front of here, it stays as 5, rather than switches to 6. Sequence. You could also put a dollar sign in front of the B, and that would fix the column, so it can't shift columns when you copy and paste things. over. Well, let's go back to run 1. The crystal violet is also going to be a 10 to 30 dilution here. So 10 to 30 dilution, and the concentration of crystal violets here in cell C, or excuse me, E3. The same thing here. This is D10, is here, over 30 dilution of E3. E3 is the original concentration. Would be the solution dilution concentration. Now, if I copy and paste this down here, D10 will go to D11, and E3 should go to E4, but since we fixed the 3, it'll stay 3. Oops, I didn't want to do that. So we can see it here. D10 went to D11, E3 stayed as E3. It's fine, that's exactly what we want. All right, and we end up with the same concentrations because I didn't change the volumes. Let's change the volumes here. In run 2, how much DI water did we use? How much sodium hydroxide? 5. And crystal violet was 10. So between run 1 and run 2, the crystal violet concentration is the same because this is going to be 10 to 30 dilution in both cases. But the sodium hydroxide, we used half as much sodium hydroxide here, and if you look at the concentration is going to be half the concentration of run 2. That's the first thing. The next thing to look at is let's take a look at the concentrations here. The concentration, this is 10 to the minus 2, this is 10 to the minus 4. And when we look at the reaction, we need a 1-to-1 mole ratio. And so there's going to be an excess reagent and a limiting reagent. What's the limiting reagent here? Is it going to be the crystal violet or the hydroxide? Well, crystal violet is 10 to the minus 4 molar. This is 10 to the minus 2. We need equal molar. And so the limiting reagent is going to be crystal violet. In fact, for crystal violet, we only need 10 to the minus 4 molar hydroxide, but we have much, much more hydroxide. And so hydroxide is in large excess. In other words, this is a stoichiometric, 1-to-1 ratio. However, this is not a stoichiometric mix here. We have a lot more hydroxide. There's a reason we have a lot more hydroxide. We want to keep the hydroxide concentration very high. Because if we keep the hydroxide ion concentration very high relative to the crystal violet concentration, then we can do what? What's a reason we might keep one of the concentrations or more, one or more concentrations very high? The reason is for pseudo M order. If the hydroxide ion concentration is very high, then maybe it doesn't change much over the course of the reaction. And so why would we want to do that? Well, the reason we'd want to do that is because if we look at the rate's going to depend on the crystal violet and the hydroxide ion concentration. When we look at this curve is actually the absorbance, but it could be the concentration. Concentration is directly proportional to absorbance. But when we look at this curve here, this curve is going to be a composite. Because even though what we're watching is the crystal violet, let's say we started off with 1 molar crystal violet and 1 molar hydroxide. So if we cut the crystal violet concentration in half, and so we went from 1 molar to half a molar, then the hydroxide concentration would go from 1 molar to half a molar. In other words, as the crystal violet concentration goes down, so does the hydroxide concentration. And so what we see here is we see the overall order of the reaction. And did we already look at this curve before? This curve looks to be a what order curve? Zero order? Let's blow it up. Here, I'm just going to plot. Make a new plot. Excuse me, zero order, the concentration versus time, I didn't label it, but the concentration versus time plot should be linear. And so this is not linear. For first order, you know, in other words, we can also do half-life analysis. For zero order, half-life should be cut in half each successive time. For first order, half-life should be about the same. For second order, the half-life doubles each successive time. So let's take a look at the half-life here. Let's say we're starting around 1200, we go to about 600. So the first half-life took about this long, you know, 1, 2, 3, 3.5 blocks. And then we look at the next half-life. So we go from about 600 here to half of that is about 300 here. So let's take a look. That's going to take 1, 2, 3.5 blocks. Do you see the half-life is approximately the same? Well, it's kind of hard to eyeball the half-life. There's a better way to do that. And the better way to do that is to make some additional plots. How many points do we need to define a curve? 3. But when you do only 3 points, you have to be really careful because 3 points can lead to error. 3 points can lead to much more significant uncertainty and error because of random error. And so if I pick the first 3 points, does that look like a first order decay to you? No. And so we have to be careful. So obviously the more points we have, the less uncertainty, and the less error we associate. So we always have to be careful. It's better to have 3 points that are far apart than 3 points that are clustered close together. But anyway, we have plenty of points in this. And so what we'll do here is we'll make a few more plots, 2 more plots, to see. And so these are the 2 more plots. We're going to take the ln of the concentration. Actually, this is concentration now of crystal violet versus time. That looks pretty linear. And then we're going to take the ln of A, not the ln of A, that we just did that. 1 over A versus time. This doesn't look so linear. And so this looks linear, but how do we quantify it? The way we quantify it is by taking a trend line. And so we'll insert a trend line here, which is the black line. And then we'll see how well our individual data points, the blue dots, line up with the trend line. The trend line equation is given by this, and this r squared value tells us how well the data matches that trend line. For example, if every blue dot lines up on the line, then r squared would be 1. It would be perfect correlation. This is close. I mean, it's 0.997. And so we got 3 nines here. So the correlation is pretty good. Whereas down here, you can see clearly this is not linear, because most of the dots do not line up on the line, the black line. And so here's the black line, the equations for that. But when we look at the r squared value, the correlation factor, it's 0.94. 0.94, an R squared or correlation factor 0.94 does not mean 94% of the dots lined there. It means that it's not very good correlation. It's not a very good fit. If we go back to the concentration versus time, or in this case absorbance versus time, absorbance and concentration is directly proportional. We see that the correlation's poor. You know, this is not very linear. R squared is 0.94. And so it looks like the ln of A is the best fit for our data. And so if the ln of A versus time plot is linear, then we say that it is first order. And so this would be first order. But is it first order in crystal violet, or is it first order overall? We say it's first order overall. First order overall means that as the crystal violet changes, so does the hydroxide. As both of those changes, the net impact is its first order. And so it looks like M plus N equals 1. Overall, the reaction is first order. But, you know, that brings up a problem because we don't know what M and N are, and we only have one equation and two unknowns, so we can't figure it out. And so we have to remove one of these. And the way we remove it is the influence of one of these. And the way we remove it is by doing it pseudo-M order. And so what we're going to do is we're going to get the hydroxide concentration so big that it stays essentially constant throughout the course of the reaction. And so what we want to do is we want to make the hydroxide concentration so big it stays fairly constant, and then we'll absorb it into the K. We'll call the K prime. And K prime is going to equal our original rate constant times the hydroxide raised to the n power. We can show that the hydroxide is fairly constant by calculation. So let's take a look at run 1. If we look at run 1, the initial crystal violet concentration is 1.3 times 10 to the minus 4. The hydroxide ion concentration is 0.0339. And so let's consume 90%. If we consume 90% of our crystal violet, which is limiting reactant, we're going to be left over with 10%. And so when the crystal violet is reacted, when 90% of the crystal violet is reacted, what percentage of the hydroxide has? And so this is the change. It's a 1-to-1 ratio. And so we lose this much of the hydroxide. And that turns out to only be a 0.3% change. And so 90% of the crystal violet is reacted, but only 0.3% of the hydroxide is reacted. And so that means the hydroxide concentration barely changes through the course of the experiment. If the hydroxide ion concentration barely changes through the course of the experiment, then the hydroxide concentration is a constant. The only thing that's changing the rate, that is the slope, is the crystal violet concentration. And so when we go back to the plot here, we see that the only thing changing the rate, that is the slope, is the decrease in the crystal violet concentration. The hydroxide concentration is so high that at the beginning of the reaction versus the end of the reaction, the hydroxide barely changed. Barely changed. And so in this way, we can easily see what M is. M is going to be 1. It's first order. Let's take a look at run 2. For run 2, when we have 90% of the crystal violet react, only 0.7% of the hydroxide is reacted. So again, very little change in the hydroxide. The hydroxide concentration is fairly constant, and therefore the rate and the slopes of the plots only depend on the crystal violet concentration changing. So for this, we're going to get m and k prime from the graph. So the slope is just equal to k. And since we're doing it pseudo m order, k is k prime. And so it looks like the ln versus t plot, ln were the most linear. Run 1 was 999, run 2 had 999s. The other plots had poor correlations with an r squared value less than 0.95. And so those weren't so well correlated. And so if we look at the plots and we get the slope, and we just change the sign. So this gives us a k prime. And you can see what happens to k when we double the concentration of hydroxide. This is actually backwards. This is for different volumes, but essentially when we double the hydroxide, what did we do? Going from run 1 to run 2, so what's right? Run 1 had twice the hydroxide concentration as run 2, so when we double the hydroxide, what happened to the rate constant? Looks like the rate constant more than doubled. So let's figure out the order. So we can get the k from there by solving this equation, and we'll end up, the k for these are the same. The k primes are different because of the different amounts of hydroxide. And then we'll solve for the n using this math here. I'll skip the details. And so then we come up with this. And so once we have this information, this is what we get. We get k is going to come from the graphs. For the graphs, they're going to give us k prime, and then k we're going to just solve based on what we call or define as k prime. M we get from the graphs, which one was most linear? It was natural log. And we get from using this math here. The math, because the numbers aren't so clean, because normally when the numbers are clean, like you double the hydroxide, the rate doubles, the rate quadruples, or the rate stays the same. Now that's clean, but when the rate does something other than those, then we'll use this math here to calculate it. Just solve for n. And so I'll talk about this more when we go to the computer lab next week on Tuesday. What I want to do now is I just want to go through, so that's just to get you thinking about the kinetics calculations, what we just talked about, but I want to just finish up chapter 14 at this time. And we were talking about this particular reaction, the hydrogen plus the 2 ICLs. Did we do this one? So mechanism was postulated, and we just verified that it was correct. This first step was slow. Second step was fast. The slow step dictates the rate of reaction. And so the rate of the first step, which is a simple collision, just depends on one molecule of H2 and one molecule of ICL. So it's first order in H2, first order in ICL. So with any mechanism, we have to make sure that the steps add up to the same net reaction, which it does. And we have to make sure that the experimental rate law matches our rate law that we derive from the mechanism. This step we don't care about necessarily because this step is fast. So I think we left off with this reaction here. This reaction. And did we already come up with a two-step mechanism for this? No.
I think we did this one.
Did we finish it?
No.
No.
We didn't start.
We didn't start it yet? Well, let's take a look at this reaction here. We might try a simple mechanism like the one we saw earlier, in which the first step is slow. And the problem is here, if we have this would be a 3-molecule collision. If this happened in one step, we'd have a termolecular collision. The rate law looks like it's okay. This is the rate, delta P over delta T, delta concentration of products. This is equal to K NO squared O2. And so it looks like we need 2 molecules of NO, 1 molecule of O2. We could have it, but we would have to have a single 3-molecule collision. And a single 3-molecule collision, is that very probable? No, it's highly improbable. So we'd start looking for other collisions. And the other collisions would be this. Maybe we have 2 NOs collide in a bimolecular collision. If 2 NOs collide in a bimolecular collision, we call that first step slow. Then the rate law would just be NO squared. Or if we have 1 NO and 1 O2 collide in bimolecular collision, then it would be first order in NO. Oh, this is wrong. This is not NO2. This should be NO. And so we try different things. What happens is none of those work out until we come up with this mechanism. A lot of trial and error went into this point here. But once we figure out the correct first one, well, we don't know if it's correct. There could be other ones. Once we figure out a plausible first step here, that is 2 NOs collide to form an N2O2. That seems reasonable. Then this would be our first step. This cannot be the slow step, because if this were the slow step, then there's no O2 dependence here. And experimentally, we do have an O2 dependence here. We'll go to the next step. The next step is an N2O2 collides with an oxygen. This is a simple collision and forms 2 NO2s. This one we'll call the slow step. And so these 2 steps have to add up to the net reaction, which they do. And 2, the rate law that we get from this proposed mechanism has to agree with the rate law we get from experiment here. And so what is the rate law that we get from this? Well, the rate law is going to be the rate of the slowest step, which is the rate determining step that we have here. It's not in sequence. And so the rate of the slow step here, this is the rate of production, O2 production, is equal to K2, the rate constant for this, times the N2O2 concentration, is here, to the first power, times the O2 concentration to the first power. So it looks like the rate of the slow step here is first order in N2O2, first order in O2. But does this rate match the experimentally observed rate? And the answer is no, they don't. And so if theory and experiment conflict, which one wins, theory or experiment? As long as the experiment was done correctly, experiment wins. And so this looks to be wrong. But what you have to know is this turns out to be right. What you have to know is that intermediates aren't allowed in the rate law. Okay, what we want are just the reactants. And so this N2O2, we have to get rid of that. Well, the only way we can get rid of that is, well, there are two ways. When we have a second slow step, we have two possibilities for the first step. The first step, possibility number one, is what we call what we call fast reversible here. Fast reversible. And so the two scenarios you're going to run into when we're dealing with a second step that's slow. It's like this. So we have a two-step mechanism. We could have more than two steps, 2+ step mechanism. Second step is slow. That is, the second step is the RDS, the rate determining step. And so step one doesn't dictate the rate. Step two dictates the rate. And so the rate of step 2 is equal to the rate of the overall reaction. But in order to get the rate of the overall reaction, we have to look at step 1. There are two ways to deal with step 1. The first way is using fast reversible. The second way of doing this is by using the steady state approximation. Okay, we're going to do it both ways. Let's see what happens. So the first way here is we're going to say that the first step is fast and reversible. And so fast means the K's are big. Reversible means the forward and the reverse direction are both occurring. And so the rate constant that we use, in the forward direction we'll use the rate constant K1, in the reverse direction we'll use the rate constant K minus 1. And what we're going to say is that this is fast reversible and at equilibrium, so that such that the rate of the forward reaction is equal to the rate of the reverse reaction. So they skipped a step here. And so the rate of the forward is equal to the rate of the reverse. Well, the rate of the forward reaction is going to equal K1, the rate constant in the forward direction. And this is simple collision as well, so it's just going to be dependent on two molecules of NO. So in other words, we'll have NO squared, left NO and right NO that are going to be colliding. So that's the rate of the forward. And what we're going to say is that rate of the forward reaction is going to equal the rate of the reverse reaction. The rate of reverse reaction is going to be K minus 1 times the N2O2 concentration to the first. We just have one molecule. It would be unimolecular. So that's what we get. Now, what we're going to do is we're going to solve this equation for N2O2. When we solve the equation for N2O2, we get that the N2O2 is, we just divide both sides by K minus 1. It would be K1 divided by K minus 1 times the NO squared. So just simplify this equation, that's what we get. Your book does a couple of other things here. Well, let me show you. This K1 over K minus 1, your book is going to call capital K. But ignore that because they don't change it. So over here they just should. So ignore this equation here as well. And then all we want to do is once we solve it for N2O4, we want to substitute it here because the N2O4 is what we call an intermediate product. And we don't want the intermediate product showing in the rate law. The rate law should depend on NO and O2. And so you're going to get N2O2 in terms of NO here. And so we'll substitute this in here. And in fact, the book ignores this, what they just did with the capital K, because they don't use capital K there. And so we'll substitute that here. We're going to get K2 here, and then K1 over K minus 1, K1 over K minus 1, NO squared, and then that's going to be times the O2 here. K2, K1, K minus 1, we can combine into one constant, which we'll call K prime. So K prime will be K observed here. And then when we look at the kinetics, is second order in NO, first order in O2, first order in O2. And so now this mechanism, the rate law we derive from this mechanism, is consistent with the experimentally observed rate law, and they match. And so what we can say is that this proves that this is a plausible mechanism. It doesn't prove that this is the correct mechanism because we might be able to think of other collisions that might give us the same net reaction and might actually give us the same rate law. And so for proof, we'd need additional work. All right, that's fast and reversible. The other way of handling this is via the steady state approximation. And we'll do that after we take a break. So let's take a break now.